Nicotinamide mononucleotide (NMN), by replenishing intracellular NAD+ levels, offers a compelling route to restore autophagy in tissues that are central to metabolic regulation, namely the liver, skeletal muscle, and adipose tissue. These organs each suffer distinct yet interconnected forms of decline with aging and obesity, and their ability to respond to metabolic stress is closely tied to the status of autophagy. While NMN supplementation can stimulate autophagic pathways across multiple tissues, the response is not uniform. Instead, it reflects the unique roles, vulnerabilities, and regulatory architecture of each tissue type. Understanding these differences is key to harnessing NMN's full therapeutic potential and designing targeted interventions to improve whole-body metabolic health during aging. In the liver, NMN shows a robust and well-characterized capacity to enhance autophagy, particularly lipophagy and mitophagy, two processes that are impaired in aging and fatty liver disease. The liver is especially sensitive to NAD+ levels because it serves as a hub for detoxification, lipid handling, and glucose production. In aged or obese states, hepatic autophagy becomes inefficient, leading to lipid accumulation, steatosis, inflammation, and insulin resistance. NMN administration restores NAD+ availability, which activates SIRT1 and DMPK, two key regulators of autophagy. This leads to the upregulation of genes involved in lysosomal function and the breakdown of lipid droplets, improving hepatic insulin sensitivity and reducing fat buildup. Importantly, NMN has been shown to reduce liver inflammation and oxidative stress through mitophagy, which clears damaged mitochondria and prevents excess reactive oxygen species (ROS) generation. Among the metabolic tissues, the liver may be the most responsive to NMN's autophagy-promoting effects, likely due to its high metabolic plasticity and central role in nutrient sensing. Skeletal muscle exhibits a more nuanced response. Muscle aging is characterized by a gradual decline in mitochondrial quality, reduced protein turnover, and impaired regenerative capacity, factors that contribute to sarcopenia and metabolic inflexibility. Autophagy in muscle is vital not only for mitochondrial maintenance, but also for the removal of dysfunctional proteins that can impair contractility and energy efficiency. NMN elevates muscle NAD+ levels and stimulates SIRT1 and SIRT3, which promote both general autophagy and mitophagy. Studies in aged mice show that NMN improves mitochondrial respiration and endurance capacity, partially through the increased expression of autophagy-related genes such as LC3 and BECLN1. However, the activation of autophagy in muscle seems to require longer NMN exposure or combined stimuli like exercise or caloric restriction to reach maximal effect. While the liver responds quickly and directly to NMN alone, skeletal muscle may require synergistic metabolic cues to fully engage its autophagic potential. Adipose tissue presents a more complex and context-dependent response. White adipose tissue, WAT, especially in visceral depots, becomes inflamed and dysfunctional with age, characterized by reduced lipolysis, increased fibrosis, and immune cell infiltration. Autophagy in adipocytes is essential for lipid droplet turnover, mitochondrial function, and thermogenic capacity. NMN administration in aged or obese models leads to improved insulin signaling and reduced inflammation in WAT, but the autophagic response appears to vary depending on depot location and the existing degree of metabolic dysfunction. In subcutaneous fat, NMN can promote the browning process, converting white adipocytes into beige, energy-burning cells, through enhanced autophagy and mitochondrial biogenesis. In visceral fat, where inflammation is more entrenched, NMN may first act by suppressing NF-B signaling and reducing senescent cell load before fully restoring autophagic flux. Moreover, NMN seems to influence the phenotype of resident immune cells, steering macrophages away from a pro-inflammatory state and thereby creating a more permissive environment for adipocyte autophagy to function properly. Collectively, these tissue-specific effects reflect both the strengths and limitations of NMN as a systemic metabolic enhancer. The liver, with its dynamic metabolic role, responds rapidly and thoroughly to NMN-induced autophagy. Muscle requires sustained intervention and may benefit most when NMN is paired with physical activity or nutrient challenges that naturally stimulate autophagic turnover. Adipose tissue, particularly visceral fat, shows a slower but significant response as inflammation subsides and metabolic tone improves. Yet in all three tissues, Autophagy functions not just as a waste disposal system, but as a critical regulatory mechanism for adapting to energy stress, repairing damage, and maintaining homeostasis. This nuanced understanding highlights the potential of NMN not as a one-size-fits-all solution, but as a precision tool for metabolic renewal, capable of reawakening tissue-specific autophagic programs that decline with age. By tailoring interventions to tissue context and combining NMN with lifestyle or dietary strategies, it may be possible to orchestrate a coordinated rejuvenation of metabolic organs. Such a strategy holds promise not only for combating age-related obesity and metabolic disease, but also for extending the years of functional health that define quality aging.